It's September of 2007 on the Google campus in Mountain View. 3 engineers are sitting around waiting for a C++ program to compile. And this is not some toy program. It's one of Google's giant server binaries, the kind that pulls in thousands of files and takes the build farm somewhere between 30 and 45 minutes to churn through. There's nothing to do but wait. You drink coffee. You complain. But somewhere in that waiting room, a thought is forming. What if the problem isn't the build farm at all? Because the 3 engineers doing the waiting are not ordinary engineers. Thompson created Unix and the B language, the direct ancestor of C. Pike co-created UTF-8 and built Plan 9, Bell Labs' successor to Unix. And Griesemer worked on the V8 JavaScript engine and studied under Niklaus Wirth, the designer of Pascal. 4 decades of language and operating system design stuck in the same build queue, and the conclusion they reached was unusual. The build farm was enormous. The problem was the language. So while the compiler ran, they started sketching a new one. By the end of the day, it had a name: Go. Here's what made their sketch different from almost every other language design. Most languages are built around one question: how do we make code easier to write? More expressive types, more powerful abstractions, more elegant ways to say the same thing. At Google, that question missed the point. Code there outlives its author. The person debugging your service at 3 in the morning is not you. And engineer number 4001 has to read code written by engineers 1 through 4000. At that scale, the writing experience barely matters. What matters is whether a stranger can open any file in the repository and understand it. So hold on to this frame because the entire course hangs off it. Go optimizes for the reader. Pike said it directly. This is a language designed in the service of software engineering, not language research, not elegance for its own sake. The unglamorous day 2 problems: building, reading, maintaining, and changing software with many hands over many years. Every decision you're about to see falls out of that one sentence. When it launched, the loudest criticism was everything it didn't have. No inheritance, no exceptions, no operator overloading, no ternary operator. For 13 years, no generics. Critics called it a language stuck in the 70s. But every omission was a decision, and they all serve the reader. The spec is tiny, exactly 25 keywords, where C++ has nearly 100. You can read the entire language specification in an afternoon, and people actually do. A small language means the code you meet in the wild uses the same constructs you learned. There are no dialects. There is no clever subset that someone else knows and you don't. Take the most basic thing a language does: repeating work. There's exactly one loop keyword: for. Watch it cover everything. With just a condition, it's a while loop. Drop the condition, and it runs forever until something breaks out. Add the range clause, and it walks a collection, handing you the index and the value. 3 jobs, 1 construct. Nothing to argue about in code review because there is no second way to do it. And multiply that by the whole language. 2 Go programmers, given the same problem, tend to write eerily similar code. That sounds boring. It is boring. It's also exactly what you want when your job is reading code someone else produced. Formatting got the same treatment. This file compiles fine, but the indentation is chaos. The braces drift. The spacing is random. Every other language settles this with a style guide and 1,000 code review comments. Here, you run one tool: Go format. No configuration, no options, no debate. The file snaps into the one canonical style, the same style as every Go file on the planet. Tabs versus spaces, brace placement, alignment, all settled, permanently, for everyone. 20 years of formatting arguments deleted by a single command. And because every file looks the same, your eyes learn to parse the language fast. Familiarity is a feature, and here, it's automated. Now the decision that shapes daily life more than any other. What happens when things fail? Most languages route failure through an invisible side channel. Exceptions, erupting from any line, teleporting control 3 files away to whatever handler catches them. Here, errors are just values. A function that can fail returns its result, and an error side by side. Look at this read. os.read file hands back the file's bytes, and error. If something went wrong, error is not nil, and you handle it right there, wrapping it with context about what you were doing. Read those 4 lines the way a reviewer would. The function might fail. You can see that it might fail. You can see exactly what happens when it does. Nothing is hidden. Yes, you will write if error is not nil hundreds of times in this course, but every failure path sits visible on the page. Remember that. It pays off at the end of this lesson. And the 45-minute wait that started all of this? Engineered away at the root. The import system was designed so the compiler never rereads what it doesn't need, which was the exact disease that made C++ builds crawl. Watch a real service build. Done. Seconds, not minutes, and definitely not 45 of them. You'll feel this every single lesson. Change, build, run is a loop you go around in under 10 seconds, and that tight loop is where learning actually happens. There's one place the designers added instead of subtracted, and the timing explains it. Around 2005, the free lunch ended. For decades, chips doubled in speed every couple of years, and your code got faster for free. Then, physics said no. Clock speeds flatlined, and manufacturers started shipping more cores instead of faster ones. All new compute was parallel compute, and mainstream languages handled it with threads and locks. Easy to get wrong, miserable to debug. The answer here reaches back to 1978, to Tony Hoare's communicating sequential processes. Lots of small independent processes talking to each other through channels. They became Go routines, cheap enough to run 1 million of them on a laptop, and starting one takes a single word, Go. That's all I'll say for now. Module 5 is 6 full lessons of exactly this machinery. Public release came in 2009, but the move that mattered came in 2012, version 1, and with it, the compatibility promise. Code that compiles under Go 1 keeps compiling under every future release. A program from 2012 builds today on 1.26, 14 years later, usually without touching a line. If you've lived through Python 2 to 3, you know how rare that is. Companies noticed. You could bet a code base on this language, and the ground would not move under you. And then, it quietly won an entire layer of the industry. 2013, a small company rewrites its container tool, Docker. 2014, Google open sources its cluster orchestrator, Kubernetes. Terraform, Prometheus. The tooling that builds, ships, and monitors modern software is, to a remarkable degree, written in one language. Nobody announced it. The cloud just turned out to be written in Go. Which brings us to now, and the reason this course exists in 2026. Think about how you actually write code today. An AI writes the first draft. You describe what you want, code appears, and your job shifts from typing it to judging it. Is it correct? Is it safe to ship? Does it handle the failure cases? The bottleneck has moved from writing code to reviewing it. Now, replay everything from the last few minutes with that shift in mind. A language that optimizes for the reader when you just became a full-time reader. One idiom, so machine-generated code looks like all other code, and deviations stand out on sight. A tool chain that is entirely mechanical. The formatter normalizes style, vet flags suspicious constructs, the compiler enforces types, the race detector catches concurrency bugs. Every one of those checks is a program, which means an AI agent can run them, read the errors, and fix its own output, in compile cycles measured in seconds. A Google-scale codebase and an AI assistant are the same problem. Lots of code, written by hands that aren't yours, that you must read, verify, and maintain. This language was built for that problem. 17 years before it became everyone's problem. Let's be honest about the trade. because this course will be honest the whole way through. It's verbose. You will type if air is not nil until your fingers do it on their own. It's conservative. Generics took 13 years to arrive because the team refused to ship a design that compromised the rest of the language. And it's not for everything. Native UIs? No. Data science lives in Python. If you want a type system you can prove theorems in, Rust is down the hall. The bet is that boring is a feature. The language is small enough to stop thinking about, so your attention goes to the system you're building. Here's how the rest of this course works. One project built end-to-end. It's called feedstack, a feed aggregator that starts life as a tiny command line program fetching a single feed and grows, lesson by lesson, into a tested, configured, concurrent HTTP service, pulling dozens of sources at once, deduplicating them, and serving one combined feed. Every feature you learn exists because the project needs it. Module 2 gives you the building blocks: values, control flow, functions, pointers, slices, maps, structs. Module 3 talks to the world: errors, files, I/O, real APIs. Module 4 models with types: methods, interfaces, generics. Module 5 does many things at once. And Module 6 ships it: tests, fuzzing, the HTTP server, observability. First, though, we need the toolchain on your machine. There's a tool that makes installing language toolchains almost unfairly easy. That's next.